Okay, thanks for the introduction and good afternoon to everyone. So with this talk, we are gonna change a little bit the context of application of additive manufacturing technology, since we move to the medical context and in particular to surgical simulation. In this talk, we are gonna see the most promising materials for this kind of activity, and we will see the approach we follow to come up with a material characterization aimed at the implementation of a suitable constitutive model into commercial finite element software. Let me start from a brief contextualization of the activity. You may be aware that additive manufacturing in recent years has gained more and more importance into the medical context, especially as what concern the medical prototyping activity. With medical prototyping, we define the activity of producing an anatomical replica thanks to 3D printing of a patient-specific anatomical district that we can reconstruct starting from the patient-specific image dataset like CT scan or MRI through a process called image segmentation. Here in Pavia, this activity started as a research activity, but today it is becoming more and more a clinical application. We gave birth a few years ago to 3D4Med, that is the first clinical 3D printing lab. So a laboratory placed inside the hospital entirely devoted to the production of such models for different applications, patient counseling, didactic purposes, training, and so on. So just to say that this is gonna enter stably in the forthcoming years into the medical context for a number of different applications. So regardless to the specific district and application, so we work with a lot of different surgical specialties. Beside the specific application, we can simply divide the production of the lab and more in general the medical prototyping activity into two groups. On one hand, we have the surgical planning. So in this case, the 3D printed model is intended to replicate the morphology of the anatomy. So we are interested mainly in the visualization of what we already saw on the CT scan and or on the MRI. On the other hand, we have the surgical simulation. So in this second case, morphology is important, of course, but material plays a major role, since in this case, the surgeon is going to interact with the model, since he wants to perform in advance the entire surgical procedure he is going to perform on the actual patient. We have to say that models for surgical planning have been produced for years without the use of 3D printing, but we have also to point out that they have some important limitation currently. They are usually made out of standard or simplified anatomies, and they are mechanically or geometrically optimized, commonly not both. So looking at the standard today as a platform for surgical training, we know that we can reach high morphological realism, but we still lack in the correct sensory feedback the platform gives to the surgeon, and a lack in the simulation of the tissue response. Why I'm pointing out those issues? Because surgical simulation is a very complex task in which the surgeon needs to develop a fine ability, a fine sensibility in the interaction with very fine and subtle structures. Here in the video, you are looking at an entirely 3D printed platform we produced, in which we optimize from an experimental point of view the performance of the vessels for the suturing. So, given the context and given the importance of the materials for an effective training, since if the material is not very well performant, we will always have a training phase that needs to be carried out in vivo or ex vivo with all the limitation and difficulties that we know. So in this context, the most promising materials and technologies are photopolymers and material jetting. Photopolymers, because in this group of materials, we have highly deformable materials that are well suited to simulate the mechanics of soft biological tissues. And thanks to the material jetting approach, with those materials, we are also able to tune the stiffness thanks to the generation of the so-called digital materials. Just to recall the concept behind material jetting, in this technology, we start from 2 or more materials that can be combined at a micrometer scale thanks to the combination, to the local combination of drops of each material. So looking at the concept, we can immediately understand that we have infinite possibilities in the development of new material formulation. Varying the base materials, of course, the percentages of each material, and also the spatial organization of droplets, creating also microstructures inside a base matrix. So we know that those materials are extremely important, can be effectively used for the surgical simulation activity, but we also know that material optimization for the different surgical tasks is commonly done just on an experimental basis that can be qualitative, that means that is done relying on the feedback of the surgeon for the specific task, or quantitative, so performing a tailored mechanical characterization of the material and comparing it to the performance of a biological tissue. And usually we rely on a porcine model to do this. We also know that soft rubber-like materials like deformable photopolymers are known to have a not negligible viscoelastic behavior. But if we look at the literature about photopolymers used in material jetting technology, we will see how they are mainly described through linear elastic models or pure hyperelastic model. So completely neglecting the dependence from time of those of their response. So the goal in this context for us was to find a methodology which allow us to perform an experimental evaluation of the parameter of a suitable constitutive model to be used for material jetting photopolymers. And we wanted also to find a formulation that was already implemented in the most common finite element software. So to directly move from the mechanical characterization possibly to the implementation. To develop this methodology, we focused on 10 photopolymers from Stratasys, that is one of the major players in material jetting 3D printers production, including 2 base materials. One is the Versian, that is a rigid material characterized by a short D of 83, and the Agilus 30, that is the most deformable photopolymers available in this machine, so a highly flexible material with a short A of 30. And 8 combination, so 8 digital materials coming from those 2 base materials that can be named after their short A value. And you can see the 2 base materials and how the blue shades from the Cyan to the Agilus thanks to the different percentage of the 2 materials combined at a microscale level. We selected a constitutive model, in particular a viscoelastic model expressed highlighting the contribution of the shear relaxation modulus and the bulk relaxation modulus. And for this particular aim, we consider that the material incompressible, so neglecting the dependency of K from the time. And we selected a particular expression of the model by means of Prony series. And this is done, this comes from the fact that one goal was to find a formulation that was available in the majority of finite element commercial software, and the Prony series expression is one of them, so is available. Our goal is then to find the form determine through experimental testing campaign the value of the shear relaxation modulus. We did that thanks to a characterization based on a rheometer. So we had to perform a characterization in which we were able to acquire the shear response in frequency. So we performed the characterization at different temperatures. Each time we applied a sinusoidal strain history thanks to the rheometer in the range of 100 Hertz. We acquired the shear stress and we computed the shear relaxation modulus. And then we raised the temperature and we performed all the other characterization. This is an example of what we can achieve from the mechanical testing, so the storage and the loss modulus in frequency domain for different temperatures. Here we are looking at a single material, in particular the Agilus 30 material. Starting from this group of curves acquired at different temperatures, we need to compute the so-called master curve, and we did that thanks to the William-Lander-Ferry approach. This approach is valid until 50 degrees above the glass transition temperature, and under the hypothesis of a simple polymer from the rheological point of view, we can say that a shift in temperature can be considered equivalent to a shift in frequency. So as a first test, we set as T0 the glass transition temperature, and we used two constants, C1 and C2, that we retrieved from literature for this class of polymers, but we did not get satisfactory results. As you can see in the graph here, you can see that we have no overlapping between the points, so we are not getting a very smooth master curve. We thought at the beginning that the cause was an error in the estimation of the glass transition temperature, but we verified it and we also tested a shift in the value that we were using, but we definitely found that the problem was the value of the constants, C1 and C2. So we changed the approach and we implemented the approach described in the work of Andreozzi. Here you have the reference for all the details. That is based mainly on a linear regression approach. So just to briefly go through the approach, we define a reference curve at a fixed temperature, for example, 40 degrees, and we find in all the other curves at different temperatures a value that is identical or extremely close to the value of the reference curve. This value has a shift in the frequency domain. So we compute the shift factor as the ratio between the reference and the actual curve frequency in this way. Then we do the same for all the other curves at other temperatures, and we plot the results having the shift in temperature in the x-axis and the shift in temperature over the logarithm of the shift in frequency on the y-axis, and we perform the linear regression. Putting the equation in this form, we highlight the two terms that are exactly C1 and C2 in the William-Lander-Ferri approach. And you can see that thanks to this linear regression-based approach, we were able to compute a high-quality master curve. So once reached this step, then we have to find the values of the terms in all the Maxwell elements, included the number of Maxwell elements. The number usually must be set a priori, but we found a way to avoid this imposition thanks to the Krein-Nudelman-Honnerkamp-Weiss method. You will find all the details about the implementation in the reference work from Jaloka. Here you have the reference. I just briefly describe how this method is based on. So first of all, we start from a fitting of the experimental data, since for the next steps, having noise in the data can impair completely the result. So we implemented a fitting with a complex valued function. Actually, since we implemented everything as a MATLAB code that ran from the source data to the determination of the Maxwell element factors, we had to split in the real and imaginary part fitting due to the functions available in this coding language. Then we built two additional functions starting from the first one. And beside the numerical approach to retrieve the final values, we can see also from a graphical point of view that the number of Maxwell elements can be spotted by the number of common zeros in the two functions. And moreover, the values at the zeros are the inverse value of the relaxation time. So having the relaxation time, we can compute the matrices A and B that allows the computation of the storage and loss moduli. Here we have an example of the final results that we got directly as an output of our implemented code. So you have all the values of G0 and all the values for the number of identified Maxwell elements. You can see that for Shor 85, we were able to identify just 4 elements and 5 for all the other cases. And here you have an example, again, just on the Ageless 30 material of the result of the fitting. That is good fitting beside low frequency values for in this graph, but for the loss moduli, as we had also in the other materials, not only in the Ageless 30 material. And here you have back in the time domain the results of the shear relaxation modulus for all the different materials. Here you have the first group of materials, so from the Ageless 30 towards Shor 60, and you can see that we can see differences, but materials are really close one to the other, while raising the percentage of cyan materials, so the 83B Shor material, we can see higher differences. So we have the 70 towards the 95, and here in a separated graph, so changing also the scale, we have the comparison between the 95 Shor A material and the pure rigid material. Okay, so drawing the conclusion of this talk, the methodology that we presented, we were able to find an implemented code that allows to move from the mechanical characterization thanks to a rheometer to the definition of the required parameters to use a viscoelastic model into commercial finite element software. Results show, as expected, that we have a behavior that is rate dependent, so viscoelastic effects are not negligible as commonly done in the literature about those kind of materials. So far, we focused on the experimental part of the activity, but now in the future work, we'll see for sure a validation of the model against the experimental data in order to understand how we can use those instruments to predict the behavior of those materials and of innovative materials. And then we can also explore the possibility of including hyperelasticity in the model to account also for nonlinear effect. And with this, I thank you for your attention, and I'm open for discussion.
Thank you, Stefania, and also for keeping the time perfectly. My God, it's 16:20, so we have full 20 minutes of discussion available. I do have an icebreaker question, but I wonder if it's necessary. Of course, the icebreaker question is dumb as usual. Paul, please.
Okay, if I understood correctly, I mean, the issue is that for the surgery simulation, for instance, or the training, I guess in both cases, you want that the 3D printed material, let's say, has the same sensory aspects as the native biological materials. Is that right?
Yes, they need to, let's say, perform as the biological tissue. And this can be considered of minor importance with respect to the morphology, but is not. I was making at the beginning the example of suturing. In that case, for an effective training, it is important that the behavior of the material is as much as possible in line with the one of the real tissue. Otherwise, the training will be impaired.
Yeah, and here's the question. I mean, your talk was mainly or exclusively concerned with the, let's say, substitute material, right? With the digital material that you can produce. But how do you go about the native material? I mean, how do you test that?
From a characterization point of view, we are performing peculiar characterization. For example, we are focusing mainly on suture training, and for that we are comparing the response of biological porcine aorta with the one of digital materials. Performing puncture characterization, so measuring the force required by a surgical needle to pass through the tissue. And this is an important aspect. Otherwise, the surgeon will learn, how can I say, an incorrect gesture, thanks to the stiffness of the material. So this is one type of characterization that we are carried out comparing to biological tissue. And another characterization is the resistance to stitch traction. So we perform one stitch with suture filament over the biological tissue, again, porcine aorta, and on a sample material. And then we measure the maximum force load that the material or the porcine aorta can withstand. This is another important parameter because when they are training over the vessel, they need to perform the suture as in real life. Otherwise, they will learn a different gesture. So they can seems to be minor elements, but they are exactly the reason why today we still need to perform the training for surgeons over in vivo or ex vivo or animal models. Otherwise, you will not learn the correct gesture.
Yeah, I mean, since you collaborate with the hospital there, wouldn't it also be possible to use human tissues rather than porcine?
Yeah.
Because I'm sure there's a human donor program.
No, it's not that easy because tests are not carried out inside the hospital. So from the regulation point of view, it's not easy to bring the samples from the hospital and test them outside the hospital. So it's just a normative matter, but with a protocol, we can get over this and perform tests also on human samples. We did so for other experiments, so it is possible actually.
Okay, thanks. Very interesting. Thanks a lot.
Thank you.
Mr. Shanmugam Kumar, please.
Yeah, thanks, Stephanie, for the nice talk. But I was wondering whether the Vero White is also exhibiting kind of viscoelastic behavior, because it exhibits yielding, hardening, and softening. So if you were to combine Vero White with some elastomer or rubbery polymer, something like or Tango Plus, and if you combine Tango Plus in very small quantity, do you still expect this kind of material response?
Yes, even if, okay, changing from Vero White to Vero Cyan, and in general, the whole group of rigid photopolymers, talking about materials from Stratasys. So you were mentioning a material from Stratasys, if I understand correctly. They are quite similar. The only one that exhibits a little different behavior is the Vero Clear, so the one that simulates the polypropylene. But even with Tango and Vero White or Agelus instead of Tango, you got similar results to the one that I presented. So differences are really, really small.
Thank you.
Thank you.